Hello there, statistics scholars. This is your posted online review for exam 3, which covers from the z-test all the way through the independent and paired samples t-test, including confidence intervals and effect sizes. So I just want to cover the key, most important material that will be important for the exam. Of course, know all the things, remember all the things, be able to calculate all the things that were covered in lecture, but these topics that we're going to cover in this video are the most important things. Okay, so to begin, if we think about all the different tests that we've done so far, so we start with the z-test. So that's the z-test, right? And the only thing that makes it different for a one sample t-test is that you don't know the standard deviation for the population, right? And then it becomes a little different when you do a paired samples t-test. Right? But then the form becomes almost identical again once we're dealing with a paired samples t-test. What all four of these tests have in common is on the top is your effect, and on the bottom is standard error. That's the same form for all four tests. The top is the effect, one mean minus another mean, right? The top is always the effect. Independent samples t-test, the effect is just one mean minus the other mean. For a paired samples t-test, the effect is simply the average difference between pairs. To zoom back to the one sample t-test, the effect is the difference between your sample average and the population average. It's always the same. It's effect over standard error. Just depending on which test you're doing, z-test, one sample t-test, independent sample t-test, or paired samples t-test, what we mean by the effect subtly changes, right? If we have known population, one sample z-test, one sample t-test, the effect is the average for the sample minus the average for the population over standard error. Either what standard error is specifically because you know the population standard deviation, or our estimated standard error, where we're having to estimate it with the sample standard deviation, right? It's always the same. Effect over standard error. It's always the same with all four tests. And so your task then is to figure out which test you're doing based on the kind of information that you have. So let me give you an example of a question I might ask that would call for a one sample Z or T test. So if I said to you, I know the average candy intake among 5-year-olds in a particular neighborhood. I know that the average candy intake, here I'm saying I know it. I know that in the population, the average candy intake among 5-year-olds is 6 pieces of candy a week, right? See how I'm saying mu is equal to 6? If I know that, you know you have to be doing a one sample T or Z test. If I tell you about the average of the population, then you have to be doing a one sample T or T test. Because then I might be interested in whether or not my neighborhood has a different average amount of candy intake. And so I tell you that in my neighborhood, one sample, it's actually 8. And I'm curious if that average is statistically different than that known population. You know you're doing a one sample T or Z test. And the top of your fraction is going to be x bar minus mu. And this is the effect. Now if I also tell you that the variability in the population is equal to 2, and I tell you that we're going to get a sample of, let's say, 25 kids for our one sample, well, now you know you're doing a one sample t-test. And that standard error will be 2 over the square root of 25. But if I don't tell you the population standard deviation, but rather I tell you the standard deviation of the sample, let's say I tell you it's 3, well, then all you do is pop in the sample standard deviation into the place where sigma used to be. That's the only difference between the one sample Z and t-test. So remember that. Now, a hard thing that might show up on the test is what happens if I give you both. If I give you population standard deviation and I also give you sample standard deviation. And it's really easy. If I give you population information, you have to use it. You never go with sample information if you have population information. And so in this case, even though I try to trick you by giving you 3, you're going to put into and do the z-test and not the t-test. Because that's the only difference between a one sample z and a t-test. The only difference is whether or not you know sigma. If you do know sigma, then you put it in. If you don't know sigma, you put in the standard deviation for the sample, S sub x. Only difference. But either way, this bottom part is still standard error. Still standard error. All right. So when should you do a t-test instead of a z-test? Well, then the obvious answer is you have to do a t-test instead of a z-test if you don't know the population standard deviation. If you know it, you do a z-test. And this actually subtly changes then our sampling distribution of the mean. Because before, our sampling distribution of the mean came directly from our understanding of the central limit theorem. To refresh your memory, the central limit theorem describes the characteristics of a sampling distribution of the mean. It's an infinite number of samples where I've grabbed a sample average from each one of those infinite number of samples, where in every sample there was the same number of people. Right? So the central limit theorem tells me, 1, that a sampling distribution of the mean will be normal, that the average of a bunch of averages will be equal to the population average, and that the spread of the sampling distribution will be equal to sigma over the square root of n, which is standard error. And this is true if you know sigma, right? The central limit theorem holds and is perfectly true each and every single time if you know sigma. And with a z-test you do, because you know the population standard deviation. So the kind of conclusions that you can make when you're dealing with a z-test are perfect. They're perfect conclusions based on this perfect standard deviation for the population that is known. It becomes just an extension of the central limit theorem. But what happens then if you don't know it? Uh-oh, I guess the central limit theorem doesn't work perfectly anymore. Well, does that mean we just have to throw away the whole central limit theorem? No, because there was this guy named Gossett who worked for Guinness who figured out how the standard, sampling distribution of the mean would be changed, would be slightly altered, because you were having to estimate variability. You were having to estimate variability based on your sample. And when you do that, what changes is whether or not, what changes is the perfect normality that the central limit theorem told us our sampling distribution of the mean would be, right? It's no longer going to be perfectly normal. It's going to be slightly different than normal now. And so that's the difference. Once you jump from a z-test to a t-test, your sampling distributions subtly change. They subtly change. So before, our sampling distribution of the mean, which we got to call a z-distribution, because it was the distribution, the sampling distribution of the mean that you got to use for the z-test, so we call it a z-distribution, was perfectly normal, perfectly bell-shaped, with all those wonderful known proportions where 0.68 is going to be within 1 standard deviation above and below, and 95% or 0.95 proportion is going to be within 2 above and below standard deviations. So this is the Z distribution, perfectly normal. Well, what happens though when we move from a Z-test to a T-test? That's no longer true. It's not perfectly normal anymore. And it's not radically different from normal. But when you're having to make estimates about variability, as opposed to knowing it exactly, the likelihood of getting weird, extreme samples goes up, right? Because you're having to estimate variability, extreme samples are simply more likely. And so we say that the tails are fatter, right? And fatter tails, right? Because remember, this is a probability density function, where the scores are down here, or the different numbers are down here, and how probable they are is here. So these numbers are more probable than these ones. Well, when you're having to estimate variability, the likelihood of extreme samples goes up. And so these tails are fatter because there are more samples here now. And because the tails are fatter, it's not quite as peaked, right? So it's not quite as peaked and the tails are fatter. And this makes rejecting the null hypothesis more difficult, right? This makes rejecting the null hypothesis more difficult because remember what alpha is, it's the extreme 5%. And so if I got to make the extreme 5% here, maybe at the number 1.96, and this was 5% of the Z distribution, well, that's certainly not 5% of the T distribution. That's a whole lot bigger portion of the T distribution. And so that critical value, that alpha, is going to have to shift over, right? The critical value is going to have to get larger to make sure alpha stays at whatever it is you've set it at, usually 0.05. So the key things to take away is that a T distribution that we use for all T-tests, whether they're 1 sample or 2 sample T-tests, have fatter tails, more extreme samples, more samples in those outer tails, which makes the null hypothesis more difficult to reject because the critical value has to get larger to account for the fact that there's more extreme samples in the tails. But in reality, so those are the key things to remember. Other key things to remember about the T distributions is unlike the Z distributions, there's more than one T distribution. In fact, for every single extra person in your sample, the T distribution starts to get thinner and thinner tails, right? When sample size goes up, as n gets larger, as you have more and more people that you're using for your estimate of standard error, right? Because the Z standard error morphed into the T standard error, the more and more people that are in your estimate of variability, the more and more accurate your sampling distribution is going to be, right? And so in reality, there's actually a family of T distributions, right? And as sample size goes up, as you go from 9 people to 25 people to 36 people to 100 people, this green T distribution is going to get closer and closer and closer to this black Z distribution, right? That's going to be the idea. And then the critical value is then going to shift closer and closer to back to 1.96, which, as you may recall, is the two-tailed non-directional critical value always for a Z-test when you're using an alpha of 0.05, right? And so all these terms should be ringing a bell, right? All these ideas should be ringing a bell. And these are the concepts you're going to want to focus on the most when you're preparing for your exam. And so how we report a T distribution then is based on the degrees of freedom, right? Because sample size dictates the degrees of freedom. And we talked a little bit conceptually about what degrees of freedom are, but I think it's much more important that we understand that degrees of freedom is the number of things you know, in this case the number of people you have, minus the number of things you don't know. which is the number of averages you're having to estimate, the number of standard deviations you're having to estimate. And so for a one sample t-test, to refresh your memory, how to calculate a one sample t-test? The sample average minus the population average divided by the standard deviation for the sample over the square root of n. That is going to be your one sample t-test. But when I report it, sorry, my whiteboard is fading on me. Right? You're actually going to report it something like this. So let's just give a quick example. So let's use the example I used from before. I know that the average candy intake in the population is 6. In my neighborhood, so X bar, it's 8. I know that the standard deviation for my sample is 2, and let's say I grabbed 9 kids. Right? So I've got population information for average, sample information for average, sample information for variability, and then of course I have my sample size. So I can do 8 minus 6 divided by 2 over the square root of 9. I end up with 2 over 2 over 3, or 2 divided by 0.67, which is, oh golly, I don't know. I should have brought a calculator. Pause the movie. Let me just grab my... Will it be easy to combine these files?
I think so.
Okay. I just need to have a calculator handy. Okay, hold on.
And should I stop it and start a new one?
Can you just... Hold on. Wait, I need a calculator. Hold on. Tools. There's my calculator. Alright. Alright. And just start it whenever.
It's already going.
Oh! Okay.
I could stop it and restart it.
Yeah, would you please? Alright, so where were we? That's right, I was going to do this calculation. So we have 2 divided by 0.67. So 2.99 if I round to 2 places. 2.99 if I round to 2 places. And so this then t-test, I'm going to compare to some critical value based on how many degrees of freedom? Because that's why the degrees of freedom matters now. Because how we're going to look up our critical value, which is what we compare our actual statistic to, right? That's that critical value. It's a number that cuts off that extreme 5%, that alpha portion of the tail. I'm going to compare this t-statistic to alpha. And so in this case, because how many standard deviations am I having to estimate? I'm only having to estimate 1. So the number of people I have 9 people. Degrees of freedom is 9 minus 1, or n minus 1. And so we would say t for 8 degrees of freedom, in parentheses, is 2.99. Whatever that, and then you compare that to a critical value. But let's say I had 25 people. Well, that's going to make standard error smaller, right? It's also going to make our critical value smaller, right? So it'll make our whole statistic bigger, because let's check this out. 2 divided by the square root of 25 becomes 2 divided by 2 over 5. Let's see what 2 over 5 is. 0.4. So our t now that we've increased our sample size to 25, is 2 divided by 0.4, and that is 5. Wow, so our t statistic got a lot bigger. Well, we almost doubled our sample size. So we're a lot more confident in what we find here, right? And so we're going to compare this to a critical value, but now our degrees of freedom, because n is bigger, is going to be 24. And so that critical value, you can bet, is going to be smaller. So increasing your sample size actually has two effects. Increasing your sample size makes the null hypothesis more likely to be rejected because you are decreasing standard error, but also, which makes the whole statistic bigger, that t statistic bigger, but it also is going to make your critical value smaller. This 5, the number you're going to be comparing this 5 to is now smaller because t for 24 degrees of freedom is going to look a whole lot more normal than t for 8 degrees of freedom. And the more normal it looks, the less, the fewer extreme samples there are going to be in those outer tails, the more likely it is you can reject the null hypothesis, right? That's just the idea there. The more likely it is you're going to accurately reject the null hypothesis, I should say. All right, so let's see where we're at. And of course, everything that we're talking about in this video is stuff we went over in class. So these are just the concepts you need to focus on the most, just to remind you. Low tech. Okay, but it works. All right, so the one sample t-test, degrees of freedom is always n minus 1. But for a 2 sample t-test, an independent samples t-test, degrees of freedom is n minus 2. And let's write that equation on here, and let's see if we can figure out why that would be. So for a 2 sample t-test, we have one x bar minus another x bar. Well, where did mu go? Oh, well, to refresh your memory, mu is still here, except with an independent samples t-test, you don't have any population information, right? You don't know the population average. So now we're grabbing 2 different samples, and what we're subtracting is the null hypothesis mean difference from the actual mean difference we see between 2 different groups. So let's use our candy example. Instead of comparing my neighborhood to the known population, I might compare my neighborhood to some, I don't know, some other neighborhood that I consider to be pretty typical. And so I would have x bar for my neighborhood is 8, right? But then x bar for another neighborhood might be, I don't know, 5. I don't have any population information other than to say in the null hypothesis, we say the difference between my neighborhood and the other neighborhood is 0, right? So the effect in an independent samples t-test just straight up goes away, right? This mu minus mu just goes away. And because it's almost always 0, because that's what the null says, that there will be no differences. So what you're really doing is subtracting the actual difference between your averages. You take the null hypothesis difference, which is 0, and you end up with x bar minus x bar. Because that's what the overall conceptual idea is. The null hypothesis says the population average from which my neighborhood was drawn, right? Mu sub 1 would be the population average that my neighborhood represents, whereas mu sub 2 would be the population average that the other neighborhood's average represents. The null hypothesis says that they're not different. That they're not different. And if they're not different, when you subtract one from the other, it's just 0. And so conceptually, this is what the effect is. But this mu1 minus mu2, it just goes away. And standard error also gets a little more complicated, where we have the square root, a big square root. Well, that's the same from the way standard error was before. Let's refresh our memory of what standard error used to be. Sigma over the square root of n. Look, there's still a radical. What do you know about that? But then we have this thing called pooled variance. Well, there's variability here, right? our old estimate of standard error. It's got the standard deviation there. And this is just the variance, which is the standard deviation squared. And look at that squared variance underneath this big radical here. So there's a lot of similarities here too. Divided by the square root of n. And then this is our old standard error for a one sample z-test. But now we have 1 over n plus 1 over m, where n is the individual group sample sizes. So let's say there were 20 kids in my neighborhood and 20 kids in the other neighborhood. These n's would be then 20. And pooled variance is what you then have to calculate. You either have to calculate it the easy way, which is averaging the two variances. And remember, you do have to average the variances, not the standard deviations, to average the variances. Or you have to use that complicated formula for pooled variance if the sample sizes are unequal. Happily, the sample sizes here are equal, but I think it's totally fair for you to know how to calculate pooled variance. But in this case, we can just, if we know the standard deviation for one group, or the variance for one group, let's say it's 4, and we know the variance for the other group, let's say it's 9, then we can just average out the two variances and plug that into our pooled variance estimate, right? We can do that. That is permissible and allowed as long as the sample sizes are equal between the two groups, right? And this becomes our independent samples t-test. Now, degrees of freedom in this case, because we're going to use two different variances in our estimate of standard pooled variance, becomes n minus 2. So for an independent samples t-test, degrees of freedom is n minus 2. So in this case, n is baby n plus baby n. So in this case, where there was 20 kids from my neighborhood and 20 kids from the other neighborhood, our total n is 40. Our total n is 40. And so then degrees of freedom is n, big daddy n, 40, minus 2. Because two variances went into our estimate of pooled variance. So 38. And so let's work it out. So to refresh, to recap, our overall question is my neighborhood different, right? Is my neighborhood, the kids in my neighborhood eat more candy than other kids, right? And I don't have any population information now, which is why I'm having to do an independent samples t-test. So I've compared my neighborhood to just another neighborhood that I consider to be pretty typical, right? And so then X bar is my neighborhood's 8 candies per week, and then X bar 2, 5, is some other neighborhood's average candies per week. And this is the variance. You see I have the square there, s squared, s squared. 4 is then the variance for my neighborhood. Let's call it s sub 1. X bar sub 1, 8, is the average for my neighborhood. S squared sub 1 is the variance for my neighborhood. X bar sub 2 equals 5 is the average for that other neighborhood. Let's call it, I don't know, let's call it Claudia's neighborhood. Jenny's neighborhood versus Claudia's neighborhood. And then s sub x squared, right? S sub 2 squared, the variance for Claudia's neighborhood is 9, right? X sub 2, s sub 2 squared is the variance. Average for that neighborhood, variance for that neighborhood. Average for my neighborhood, variance for my neighborhood. And the null hypothesis would say, in the population, our neighborhoods aren't different. So this becomes 0 and just goes away. And so the average number of candies in my neighborhood was 8. And so 8 gets dropped in here. And the average number of candies for Claudia's neighborhood is 5. So that gets dropped in here. And I've given you the direct variances, right? And so you can just average them to drop those in here. So I take 4 plus 9, which is 13, and I just divide it by 2 to get the average of looks like 6.5. That is the pooled variance. Now, if I had been sneaky on you and given you the standard deviations, you would have had to square those to get the variances in order to get the proper pooled variance. That's an important point that we went over in class. If I'd given you the standard deviations instead, see how I erased those little squares? See how I erased those? In order to get the pooled variance, you would have in fact had to square them first, before averaging them. It's a really important point that we talked about in class. And of course, the sample sizes are equal, which is why I can just average them together. If they've been unequal, you would have had to use that big, long, scary equation called pooled variance. All right, so we've determined that the average of 4 and 9 is 6.5. So I can just plug this in, 6.5. And the sample size for my neighborhood was 20 kids, as I said it was. Sample size for the other neighborhood was 20 kids, because I said it was, right? N sub 1, N sub 2 for the two different neighborhoods. And so Big Daddy End, all the children that ate the candy, was 40 kids. And so my degrees of freedom that I'm going to use to look up my critical value, that I'm going to compare my calculated, obtained, or observed statistic to, those are just 3 synonyms for the same idea. The degrees of freedom I'm going to use is 38. That's why I'm going to look up my critical value. And so working out this math, 8 minus 5 is 3. So that's my effect. That is my effect. And then standard error is this whole thing down here. It's always the bottom of the fraction. Always. The effect is always in the top. The standard error or error is always in the bottom. So 1 over 20 plus 1 over 20 is 1 over 40. Oh wait. No, it's not. It's 2 over 20. Apparently I can't do math. So we had 1 over 20 plus 1 over 20, and that's 2 over 20. 2 over 20. Which becomes 1 over 10. Which is 1/10, or 0.1. Please verify in your calculators that I am doing the math properly. And so then I just take 6.5 and I multiply it by 0.1. Where did 6.5 come from? That was my pooled variance. Where did 0.1 come from? Well, that was 1 over 20 plus 1 over 20. So 6.5 times 0.1 is 0.65. So standard error is the square root of 0.65. That is standard error. Which is 0.81 if I round to 2 places. So standard error is 0.81 if I round to 2 places. So our effect is 3, because that was the difference between the two neighborhoods. There was a 3 candy difference, a 3 candy effect when I compared the two different neighborhoods. That was the effect of being in 2 different neighborhoods. 3 pieces of candy on average. So awesome. So let's calculate our t-statistic then, because the t-statistic is the effect over the standard error. Just like all of our statistics, the effect over the error. So I ended with 3.70. 3.70. That is our t-statistic. That is our obtained, observed t-statistic. And we compare that to a critical value for how many degrees of freedom? 38. Because it's Big Daddy N of 40 people, 20 in the first neighborhood, 20 in the second neighborhood, 40 minus 2, because our pooled variance had 2 variances that went into it, 2 things we were estimating. The number of things you know, the number of people, minus the number of things you're having to estimate, which is the 2 different variances going into pooled variance. Right, so we've got 38 degrees of freedom. Right, so but it's still effect over standard error. So the idea behind degrees of freedom for t-test is either going to be n minus 1, one sample t-test, or a paired samples t-test, which we'll get to in a minute, or it's going to be n minus 2. Which is when you're doing an independent samples t-test. And you use the degrees of freedom to look up your critical value. So I would be comparing that 3.7 to a critical value for 38 degrees of freedom. And where would I find that critical value? In the back of your book, table A2. All right, let's see where we're at. All right, so then the last test we learned how to do was the paired samples t-test. And so what makes the paired samples t-test different is that you do have more than one sample, but only kind of. This is where you have pairs of scores that have to meet up and match up. Because you don't just grab two samples of people, right? Like you don't just grab a sample of kids from my neighborhood and then a sample of kids from another neighborhood and then compare those samples, right? It's just the average for these 20 kids and then compare that to the average of the other 20 kids. In a paired samples, also called a dependent sample, right? Also called a dependent samples t-test, paired samples or dependent samples t-test, also called repeated measures, but that's not I don't find that to be a very good name. In this scenario, each score is paired to another score. The example I like to use a lot is when you have pairs of husbands and wives, and you're asking the question, who does more housework, husbands or wives? And so we've got Angelina, Angie, and Brad. They're still together, right? Yeah. Just checking. We've got Beyonce and Jay-Z. And so notice I'm putting all the women over here and all the men over there, right? Because with a paired samples t-test, you have to have what's called distinguishable pairs. There has to be some meaningful difference between the pairs of folks. So you've got women over here and men over here. But I could also ask about older twins versus younger twins, right? Where I have older twins on one side and younger twins on the other. Or I might look at mothers compared to their own daughters. Are mothers and daughters any different? Right? The idea is you're still looking at group differences. Here you're comparing wives to husbands, but you're going to be comparing these groups where each score is paired with another score, right? And then we have Kim and Kanye. Now I'm pre-recording this, so I'm hoping that nobody has broken up since this discussion, right? And so let's say I discover that Angie does 10 hours a week and Brad does 8, and I discover that Beyonce does 11 and Jay-Z does 10. And then, of course, Kim and Kanye do none because I love picking on them because I'm a hater, right? So here we have our pairs. And so you're not going to calculate an X bar for this group. You're not going to calculate an X bar for this group. You could, but then you have to use that big, long, scary equation I showed you in lecture. No, no, no. The first step for a paired samples t-test, the most reasonable step for a paired samples t-test or a dependent samples t-test is to subtract one score from the other, to subtract these folks from these folks, to subtract the husband scores from the wives scores. So 10 minus 8 is 2, 11 minus 10 is 1, and 0 minus 0 is 0. And so now we have different scores. That's what these are. They're how Angie is different from Brad, Beyonce is different from Jay-Z, Kim is different from Kanye, right? That's the idea here, is that you have now different scores. And so our equation is based on these different scores. Once you get the different scores, you now actually have theoretically a single sample of different scores. And so the equation looks a whole lot like right? Looks a whole lot like the one sample t-test, except this what you're looking at here is the actual difference between your pairs, D bar. We have different scores here, right? The average difference between your pairs minus the null hypothesis difference. Well, the null says they won't be different. So this number becomes 0. It just goes away. Over standard error. Exactly how we calculated it before for a one sample t-test, because now we have one sample of different scores. And so I just calculate D bar. 2 plus 1 plus 0 is 3. 3 divided by n would be the average. Well, how many scores do we have here? 3 scores, because we had 3 pairs. So our sample size is based on the number of pairs that we have. So our sample size in this example is 3. So D bar is 2 plus 1 plus 0. The average of these different scores, well, 3 divided by 3, because that's how we get an average, is 1. So in this example, the average difference score is 1. The number of pairs we have is big daddy N now. It's a really important difference between the independent samples t-test and the paired samples. In independent samples, we look at the total number of people in each group and combine them to get big daddy N, right? But in a paired samples t-test, the number of independent observations you have is the number of pairs of people, the number of couples, right? And so in this case, big daddy N is 3, because we only have 3 couples. And then S sub D would be the standard deviation of these different scores. Well, the average was 1, so I get the standard deviation by, just like we've calculated it a billion times before, so I see how I'm just taking the standard deviation, subtract the average from each of these different scores, squaring those differences. So now I have the squared, and then I add those up to get the variance, and then I take the square root to get the standard deviation. Oh no, and then I add those up and divide by n minus 1 to get the variance, and then I take the square root of that to get the standard deviation of 1. That's just getting the standard deviation like we've done many, many, many times before. These are my different scores. My average, my D bar was 1. The average of these different scores. I subtracted 1 from each of these scores. I squared those different scores, right? Then I added them up to get the sums of squares, divided by n minus 1, 3 couples, n minus 1 is 2. 2 divided by 2 is 1, that's the variance. Square root of 1 is 1. So the standard deviation in this case is 1. S sub D is 1. So to get my t-test then, I take the square root of 3 first, order of operations. .73. And then I take 1 divided by 1.73. So this whole thing becomes 0.58 if I round to 2 places. So 1 divided by 0.58 ends up being 1.72. Now, that is my t-statistic, my observed, obtained, or calculated t-statistic. I'm going to have to compare that to a critical value, right? I have to compare that to a critical value. Based on how many degrees of freedom? Well, let's look at our equation for this paired samples t-test. D bar over S sub D over the square root of n. Just one S sub D, so it's going to be n minus 1 again. So to recap about degrees of freedom, one sample t-test, n minus 1. Paired samples t-test, n minus 1 for degrees of freedom. Independent samples t-test, n minus 2. Z-test, no degrees of freedom. Right? Right. And so I would compare this 1.72 t with 2 degrees of freedom only, 1.72 equals 1.72. And so I would compare this 1.72 to a critical value for 2 degrees of freedom using that table A2. That's the idea. All right, so back to how we make decisions then. Now we've refreshed our memory of how we do one sample Z and t-tests, how we calculate independent samples and paired samples t-tests. How do we then make decisions? Well, there's 2 ways to make decisions. You can either compare your calculated or obtained t-statistic to a critical value, or you can compare your p-value to alpha. They will always tell the same story. They will always tell the same story. So let's say I calculated t for, I don't know, 24 degrees of freedom, and I calculated 2.25. That's my calculated, observed t-statistic. And let's say I tell you that the critical value equals 2.01. You're going to reject the null hypothesis, because this is what you calculated, and then you looked this one up, and what you calculated was bigger. Your statistic, your calculated t-statistic was bigger than your critical value, and so you reject. Now, how did you look up this critical value? Well, you looked it up based on degrees of freedom, but also the alpha you chose. And so this critical value is going to be based on 24 degrees of freedom, sure, but also is going to be based on an alpha of, let's say, 0.05, right? This critical value you looked up of 2.01, yeah, it's based on 24 degrees of freedom, but also an alpha of 0.05, right? Right. And so if I tell you, you calculate 2.25, the critical value was 2.01, what do? You know that you reject, because what you calculated was bigger than the critical value. And now here's the challenging question. Would your p-value be bigger or smaller than alpha? And the answer is, it would be smaller. Your p-value would be smaller. The p would be less than alpha. Why? Because big extreme statistics are highly improbable if the null is true. Big statistics are highly improbable if the null is true. So big statistics come with small p-values. But let's say you'd calculated 1.72. Now you fail to reject, because this is smaller than the critical value. And your p would have to be bigger than alpha, because less extreme statistics, smaller statistics, are more probable if the null is true. So small statistics come with bigger p-values because they are more probable. But let's say on the exam I flip it around on you, because I could do it this way. Let's say I tell you, you had an alpha equal to 0.05, and your p was less than alpha. I might then ask you, what do? And you would say, I reject, because p is less than alpha. Reject the null. That must mean your obtained statistic was bigger than the critical value. It has to mean that, right? Because if you're rejecting the null hypothesis, p is less than alpha, and your obtained statistic is bigger than the critical value. But if your p-value is greater than alpha, then your obtained statistic has to be smaller than the critical value. It's like the opposite relationship. Big obtained statistics come with teeny tiny p-values. Small obtained statistics come with big p-values. Big statistics, small p-values, reject the null. Small statistics, big p-values, fail to reject. Very important concept that you need to know. I also suggest you know the 3 assumptions of the independent samples t-test and the 2 assumptions for the dependent samples t-test. To refresh your memory, in the independent samples t-test, you assume that the population is normally distributed. You assume that each of your observations, so all of your people, are completely independent of all of your other observations, so nobody knows each other, influences each other. You also assume homogeneity of variance. You assume that the variances of the 2 populations that your 2 samples came from are roughly the same, homogeneous, the same. For a dependent samples t-test, only 2 of those are the same. You assume that in the population, the difference scores are normally distributed, and you assume that each pair, each couple, is independent of each other pair or couple, but there's no homogeneity of variance assumption, which is something we talked about in class. So I would also know those. I would know those very, very well if I were you. I would know those very, very well. But 2 other things you need to know for this exam. Of course, know all the things. Know all the things. You also need to know how to calculate confidence intervals, and you need how to calculate effect sizes. So confidence intervals are always calculated the same way. It's going to be your descriptive statistic. So not your inferential statistic, not the t statistic, not the z statistic. It's not going to be that statistic. It's either going to be your average, your d-bar, or your mean difference, right? That's what you start with, right? So let's say we're going to do the confidence intervals for a z-test. And let's say my x-bar, let's use that one from the candy, right? In my neighborhood, the average number of candies is 8. X-bar equals 8. So that's where you start. You just start with your descriptive statistic. And then what you're doing is creating a confidence interval around it. A 95% confidence interval, where you're going to then say, more than just what the p-value tells you, which is whether or not to reject or fail to reject, you're actually going to get an estimate for the population. What is my best guess, my 95% confident estimate of what the real population parameter would be? Because the p-value, all it tells you is whether or not your average is different from the population average. Or in the case of the independent samples t-test, whether or not these 2 x-bars are reasonably coming from the same population or different populations, right? Whether or not they're the same or different, that's the only thing they can tell you. Same or different, same or different. That's all the p-value can tell you. But a confidence interval gives you so much richer information. It tells you, okay, so you told me that this x-bar doesn't come from the known population. It comes from its own special population. Tell me about that population. Tell me the most likely values for that real population average to be. And if you're doing a 95% confidence interval, that must mean you're using an alpha of 0.05, right? So because you have an alpha of 0.05, you're 95% confident, because 100 minus the alpha of 0.05, 1 minus 0.05 is 0.95, or 95%. 95% confidence interval. And so to do this, you start out with your descriptive statistic, and then you add and subtract, which means you're going to be both adding a number and subtracting a number from this 8. Is going to be your standard error, which is whatever was on the bottom of the fraction when you calculated your inferential statistic. No matter whether it's a one sample t-test, an independent samples t-test, a z-test, or a paired samples t-test, standard error was always in the bottom of the fraction of that inferential statistic you just calculated. Standard error times the critical value. That critical value you already looked up to figure out if you had to retain or reject the null hypothesis. That critical value. So let's...
Recording.
Alright, so to do a confidence interval then, you take the descriptive statistic, in this case, the average for my neighborhood, using that example from before, candy in my neighborhood, and you're going to add and subtract standard error times the critical value. Standard error, the bottom part of the fraction if I'm doing a z-test, right? And so I take 8, which is my sample average, minus 1 times 1.96. Well, 1 times 1.96 is just 1.96. And where did this 1 come from? I just made it up. But it's going to be the bottom part of whatever inferential statistic you just calculated. T-test, z-test, whatever. That's what standard error is, the bottom part of that fraction. And the critical value is what you look up based on your alpha and your degrees of freedom. In this case, I tell you it's 1.96. Where did that number come from? Either table A1 if you're doing a z-test, or table A2 if you're doing a t-test. And so I have 8 minus 1.96, 6.04. 8 plus 1.96, 9.96. This is my confidence interval. I can be 95% confident, 95% confident that the real number of candies that my neighborhood is meant to represent is 6.04 to 9.96. And if my test was comparing my sample average x bar of 8 to a known population average of 6, I know I can reject the null hypothesis because 6 is outside this range. Now it's just slightly outside this range, right? 6.04 is just a tiny bit above 6, but still I can reject the null hypothesis. And so that's what makes confidence intervals so powerful, is that you can know whether or not to retain or reject the null hypothesis based on whether or not the null value is within this interval or not. If it is within the interval, fail to reject. If it's not, then reject. And you have a nice range now. I can be 95% confident that the kids in my neighborhood eat between 6.04 and 9.96 pieces of candy. And that's what makes this powerful. And so I would know how to calculate confidence intervals for all of the different tests that we conducted, z-tests and t-tests. The form is always the same. The confidence interval is your descriptive statistic, not your inferential statistic, not the t-test statistic, but the average, or either the x bar or the d bar or the x bar minus the x bar. It just depends. Standard error is always the bottom of your fraction, and the critical value is always what you look up based on the degrees of freedom and the alpha, right? So it's going to be descriptive statistic plus and minus standard error times the critical value. So definitely know about confidence intervals. The last thing that you need to know, for sure, of course, know all the things, know everything. The last thing you need to know is effect sizes, Cohen's d. And essentially, if all of the inferential statistics that we did, one sample z-test, one sample t-test, independent samples t-test, paired samples t-test, was effect over standard error, that was our inferential statistic. Cohen's d is just the effect over the standard deviation. So not the standard error for the infinite number of samples, but the actual standard deviation, either from the population or for the sample, or the pooled standard deviation, right? Or the standard deviation of standard deviation, right? Depending on what test you're doing. And so here is what Cohen's d looks like for the 4 different tests, to refresh your memory. If I'm doing a one sample z-test, it's going to be x bar minus mu. See how that's the same than the t-test? But you're just going to, over sigma. Not sigma over the square root of n, but just sigma. Cohen's d. It tells you how many standard deviations these two averages are away from each other. That's what it tells you. How many standard deviations these two averages, x bar and mu, are away from each other. If you're doing a one sample t-test, Cohen's d is just x bar minus mu over s sub x. If you're doing a paired samples t-test, It's going to be x bar 1 minus x bar 2, because that's the effect over the pooled standard deviation. But remember, to get the pooled standard deviation, you have to get pooled variance first, and then take the square root of that to get pooled standard deviation. And if you're doing a paired samples t-test, Cohen's d is just d bar over s sub d, the standard deviation for the pairs of scores, for the differences between the pairs. All right, let me just make sure there's nothing else I want you guys to know for sure. Of course, you have to know all the things, remember all the things. Also remember that Cohen's d is called the standardized effect size because you're dividing by the standard deviation, not the standard error, because that would be the t-test or the z-test, but the standard deviation, and that gives us Cohen's d, called the standardized effect size. The regular effect is just the top of the fraction for the t-test or z-test. All right, so the last thing I want to just remind you of is how do you know what test to do? There's going to be a lot of problems on the exam that basically ask you that. And so remember, if I give you mu, if I give you population average, you must be doing a one sample t or z test. If I also give you the population standard deviation, sigma, then you have to be doing a one sample z test, right? If it's a one sample z or t test, then degrees of freedom is n minus 1. And so let's say I tell you the degrees of freedom is 999, you know you had 1,000 people. If I don't give you any population information, I simply tell you I'm comparing group A to group B, or group 1 to group 2, and it's clear that these people in these groups don't know each other, you have to be doing an independent samples t-test, right? And so then the degrees of freedom becomes n minus 2. And so if I tell you that the degrees of freedom is 998, then I guess you had 1,000 people, didn't you? Your sample size was 1,000. But if I don't give you population information, and it's obvious that the pairs of scores are related, meaning you're wondering if mothers are more depressed than their daughters, you're wondering if fathers are more do more housework than their sons, or you're curious if your scores on Monday are different than your scores on Friday after you take some serum that's supposed to increase your academic ability, also is going to be a paired samples t-test, where degrees of freedom is n minus 1 again, where your total sample size then is going to be one more than your degrees of freedom. And the sample size now is the number of pairs of people that you have, right? And so if you have any questions at all, of course I've posted this well in advance of the exams. You'll have time to look at this review. Please, if you have specific questions, feel free to email me, but make those questions as specific as possible so you increase the likelihood that I can address them over email. And good luck.